Okay, so this is chapter 20 review. We have 6 questions, some are a little bit longer. And I will scroll to the answers. This is already posted on Canvas, so some of you may have seen it, may have tried to do this, and of course you could have also seen the answers. These questions are repeated under answers, and that's where I'm going now, so I'm going to scroll and then go over. So, okay, actually this one is not, number 1 is not repeated, I can see. I missed that. Okay, so what is the outcome of each of the following reactions? So here we have para-ethyl nitrobenzene, and we have 2 reactions. One reaction is with permanganate, and the other one is hydrogen in presence of nickel. And so we should, of course, consider each reaction separately. Those are 2 different separate reactions. And actually just noticed ethyl group is missing in the second compound. There should have been ethyl group here. So I will have to fix that and post it again. So when we consider, it's here in the answer. So when we consider these 2 reactions, you should consider what is the reagent. And in this case, in first case, reagent is permanganate. That means oxidation reaction. And when we consider these 2 substituents, nitro group and ethyl group, only ethyl group and alkyl group can be oxidized. And alkyl groups are oxidized to carboxylic acids under these conditions, permanganate in presence of sodium hydroxide and heat. The only exception is quaternary carbon that doesn't have hydrogens, that one cannot be oxidized. But this one is obviously not quaternary, this is CH2 group. So this would be ethyl group, CH2 group, so that's oxidized to carboxylic acid. And so product is para-nitrobenzoic acid. Second reaction is actually reduction. And of the 2 functional groups, only nitro group can be reduced. And these are conditions, catalytic hydrogenation for reduction of a nitro group. Nitro group is reduced to amino group, and so benzene with amino group is aniline, and so this is aniline, and it's para-ethyl aniline as a product. So that will be first question. Second one is predict outcome of the following reaction. We have compound nitrobenzene, and reaction is with chloroethane in presence of aluminum chloride, Lewis acid. So if you consider reagents, chloroethane and aluminum chloride, that's Friedel-Crafts alkylation. So really question is, what is the product of Friedel-Crafts alkylation of nitrobenzene? And you have choices: ortho, ethyl, meta-ethyl, or para-ethyl nitrobenzenes. Obviously, this is ethyl group. So Friedel-Crafts alkylation would introduce ethyl group on benzene ring, or no reaction. And in this case, actually, answer is no reaction. And the reason for it is that Friedel-Crafts alkylation doesn't work that well. The electrophile is not very strong electrophile. Even though it's activated electrophile, it is not very strong electrophile, and benzene ring is not very strong nucleophile, particularly when it's deactivated by such strongly deactivating substituent as nitro group. So in this case, there will be no reaction. So be careful about that. Friedel-Crafts reactions don't work very well. That means alkylation and acylation don't work very well on benzene ring with deactivating substituents, with electron withdrawing substituents. Question number 3 is very similar. Predict outcome of the following reaction. And again, reaction is on nitrobenzene, but now it's chlorination. It's chlorine in the presence of aluminum chloride. So now that's activated electrophile, effectively equivalent of Cl plus or chloronium ion. And that's actually rather strong electrophile, unlike Friedel-Crafts alkylation reagent. And so that works very well on benzene rings, even if they are deactivated. And so in this case, all that we are considering are usual electronic effects. and directing effect of nitro group. Nitro group being deactivating, directs incoming substituent into meta position. And so product is metachloronitrobenzene, or B. So those were first 3 questions. Are there any questions about them? Let me check if there's anything in chat. No, I don't see anything. Okay. Question number 4. What is the product of the following reaction sequence? That's a common type of question on exam, both my exams and also other people's exams, like maybe MCAT or certainly GRE, ACS exam. In this case, actually, you have several questions wrapped into one, and you have to know answer to each of these steps. So you go step by step. You have to know answer of each reaction. So what is the product? If there is selectivity, what kind of selectivity there is, and then come up with final answer. What is the overall product? And so simply all you have to do is take pen and paper and work it step by step. And I have that here. So first step is, as we have seen already, Friedel-Crafts alkylation. It's just that in this case, starting material is benzene. And Friedel-Crafts alkylation actually works quite well on benzene ring. In fact, in this case, probably product would be polyalkylation product, but we assume simple case, kind of we simplify that a little bit. We expect you to assume that there will be mono substitution unless you're told otherwise. And so only one ethyl group is placed on benzene ring, so product of the first step is ethyl benzene. Second step is bromination with bromine. So this is not activated electrophile. Benzene ring does have activating substituents, but that's weakly activating, so it doesn't really affect benzene ring that much. What bromine in this case does is free radical substitution. It reacts in a free radical substitution reaction in benzylic position. That's activated position. Carbon attached to benzene ring. That's the most stable free radical. So this is free radical substitution, and that means benzylic bromination. Bromine is introduced in benzylic position. And so this is the product. That's result of bromination reaction. If you're observant, you may notice that this is a chirality center. But in this case, there is no chiral induction. We don't have any chiral catalyst or chiral solvent or any reason why this reaction should produce one enantiomer preferentially over another. So in this case, we don't indicate any particular stereochemistry because we expect a racemic mixture, 1-to-1 mixture of 2 enantiomers. And then third step is reaction with sodium methoxide. That's SN2 reaction. And this is actually chapter 12 from Organic 1, but you have to know that simply we cannot ignore Organic 1 and reactions you have learned in Organic 1 because you need them to be able to follow Organic 2. And so that's why you need chapters like 12 and 14, and even those earlier ones like 7 and 9 and 10. So this is SN2 reaction. It occurs with inversion of configuration, but again, since starting material was a racemic mixture, inversion really doesn't matter. It doesn't matter if reaction is stereoselective because product is also a racemic mixture. If we start with racemic mixture, we will end up with racemic mixture. What is important is that this is SN2 substitution, formation of methoxy ether, corresponding methoxy ether. So methoxy group, CH3O, replaces bromine. And now we have benzene ring that has substituent that is mildly electron donating. Oxygen is actually electron withdrawing through negative inductive effect, but we also have another carbon of that oxygen, so oxygen is withdrawing electrons from those 2 carbons. So effect is not that serious, and we also have this methyl group with electron donating effect. So we'll assume that this is actually electron donating substituent. And it's rather large group. Electron donating substituent is orthopara directing, Probably if we were to carry out experiment, you'd probably get quite a bit of meta too, but predominantly it would be orthopara-directing. If it's orthopara-directing, this is rather large substituent, about the size of isopropyl group, if not larger, which means that substitution in ortho positions will be effectively prevented due to steric hindrance, or at least impeded through steric hindrance. And so preferentially substitution occurs in para position, and we get para-nitro compound. So rather lengthy sequence, and major product would be expected to be para product. So that was rather lengthy reaction sequence. Any questions? Question number 5. Name the product of the following sequence of reactions. So that's something that could be on the test, where you have to type up the name of the product. So previous one, this one would have been easier on the test, because question like this, since you're doing test electronically, you're not providing formulas, so you would pick one out of the 4. So that would provide you quite a bit of guide, for example, for stereoselectivity and sometimes even substitution pattern, because you would have 4 choices and one of the 4 has to be correct, and so that would eliminate a lot of possible branching points where you may be thinking about other possibilities. For bromine, obviously this is not activated electrophile. It cannot substitute on benzene ring, even though this may be mildly activating substituent. So that was probably possible answers would eliminate such possibilities and various other possibilities depending on what would be other 3 answers, such as substitution, maybe in meta position or something like that. But this is alternative, where you have open-ended question. So you don't have that kind of guide or guidance where you have 4 choices and one of them have to be correct. Now you don't have any choice. You simply have to come up with your answer and name the product. So that's a little bit more challenging compared to previous question. Previous question was challenging because individual steps were pretty challenging. And so that would be maybe for quite a few of you, maybe a little bit difficult to figure out. And again, as I said, 4 choices should help a lot. In this case, you don't have that, but individual questions are maybe a little bit easier, and so that kind of compensates. So again, we start with benzene, and now we have 3 steps. As usual, you go step by step, and keep in mind that you should consider not only reaction outcome, but also whether there is selectivity, and if there is, what would be the outcome. First step is Friedel-Crafts acylation. And so that places this acyl group on benzene ring. And so that's the acyl group. Next is Clemmensen reduction, zinc in mercury, so zinc amalgam with hydrochloric acid. That's Clemmensen reduction. It reduces carbonyl group to methylene group, to CH2. So this is a way to place, in this case, butyl group on benzene. And so product is butyl benzene. Butyl group is rather large, and it's also activating. Being activating, it activates benzene ring towards substitution in ortho and para positions. Because it's large, through steric hindrance, it prevents significant substitution in ortho positions. Now, you may be considering this is, well, butyl group, it's long chain, and it may, the way I drew it, it may prevent ortho substitution here on the right side, but there is nothing on the left. And why ortho, or why this reagent, let's say SO3, cannot come from the left? Actually, because of thermal motion, this group sweeps the space. It rotates about the single bond. Rotation about single bond is free, and it's very fast. And so that group, it keeps on spinning constantly. And so it's constantly sweeping the space around this axis. And so it's preventing actually substitution in both ortho positions. And that's how you should consider steric hindrance. Not that group will be folded and moved away from particular position in a molecule, but rather that it sweeps the space. And that means when it comes to steric hydrous, you consider actually the worst possible position, worst possible outcome, or worst possible case. In this case, that it's preventing both ortho positions from being substituted. That means that only para position could be substituted, and fuming sulfuric acid is reagent for sulfonation. So product is para-butyl benzene sulfonic acid. So this is what you would need to type up as the answer. And in your case, since you're using Canvas, you don't need this para in italic. It's okay just to type P in regular font and P-butyl benzene sulfonic acid. Okay, so are there any questions about question 5? And then question 6. What is the product of the following reaction? Here we have this compound. This is actually both anisole and toluene. You can see it has methoxy group and methyl group. So you don't have to name it. You don't have to worry about naming it. But that's activated benzene ring. And this methoxy group is stronger activating substituent. It's strongly activating. This is only weakly activating. So this is the one that activates the ring. It activates the ring towards substitution in ortho and para positions, but para position is taken. So since this is strongly activating substituent, it's going to activate ring towards substitution in ortho positions towards itself. Methyl would activate towards ortho substitution towards itself, but it's weaker than methoxy, so we consider methoxy. Again, para cannot be considered in either case because two substituents are para to each other, and so para position is not available for substitution. Now, reaction is with an electrophile, and in this case, electrophile is diazonium salt. So reaction of activated benzene ring with diazonium salts gives azo compounds. Azo compounds are those compounds with nitrogen-nitrogen double bonds. Typically, because of the steric hindrance, reaction occurs in para position, para to the activating substituent. Benzene ring has to be activated, so that's better electron pair donor, better nucleophile, and then it can add to nitrogen-nitrogen triple bond of diazonium group. As I said, reaction usually occurs in para position, but if para position is taken, then even though there may be steric hindrance, reaction will occur in ortho position because that's the only one that is available. So it's orthocarbon that forms a bond to terminal nitrogen and the nitrogen of diazonium group. So even though this middle carbon, or nitrogen, sorry, this nitrogen, middle nitrogen or nitrogen attached to benzene ring is one with formal positive charge, one that is electron deficient is actually next to it. You have already seen a number of instances like that, where an atom carries formal positive charge, but actually it's atom next to it that is electron deficient. Best example is hydronium ion, H3O+. Oxygen carries formal positive charge, but actually it's hydrogens that are electron deficient. So orthocarbon forms a bond to nitrogen. This is the intermediate. This is diazonium chloride. So chloride anion is spectator ion. In this case, we can assume that chloride anion will play a role of a base. So chloride anion picks up a proton to regenerate aromatic ring. And so this is the product, azo compound. Okay, so that completes a review of chapter 20, reactions of substitute benzenes. Are there any questions?
Yeah. Would we expect it to name the diazonium salts or not really?
No, you wouldn't. Yeah, it's not that difficult to name each substituent. Well, in this case, you wouldn't know how to name this substituent because it's both anisole and toluene. But you just name each of them and then azo. Any other questions? Okay. So I'm going to stop recording here.